Hey everyone, welcome back. Today we're diving into a pretty incredible blueprint, building a generative AI patient support chatbot. We're going to literally trace the whole journey, right from foundational architecture all the way up to ironclad clinical safety. So if you're curious about how to build health tech that, truly matters without falling into the brutal traps that catch so many developers, you are in exactly the right place. Let's get into it.
Right off the bat, let's start with a bit of a cautionary tale from our sources. Get this, $180,000. That is how much a radiology group recently blew fine-tuning a massive language model on chest X-ray reports. And the kicker? 6 months later, they had to scrap the entire project. Why? Well, they realized, way too late obviously, that a much simpler off-the-shelf retrieval method would have achieved 94% of the accuracy for literally 3% of the cost. Ouch.
Okay, let's dive into this a bit deeper, because while wasting money is obviously bad, risking patient safety is, well, it's far worse. Recent clinical simulations showed that 34.4% of emotionally vulnerable users actually experienced measurable psychological deterioration when interacting with standard, popular character-based chatbots. You see, building for healthcare is fundamentally different from building some standard customer service bot. Getting it wrong here has real human consequences.
To build a system that's both cost-effective and clinically safe, we're going to follow this roadmap, the medical chatbot revolution. Choosing the right architecture, protecting patient data, ensuring clinical safety, and finally, testing and deployment.
Section 1. The medical chatbot revolution. The medical era.
So, the AI revolution in healthcare is undeniable. In a recent study testing responses on a public medical forum, independent evaluators actually preferred a chatbot's answers over those from real, qualified physicians in nearly 80% of cases. That is wild. AI can deliver this unprecedented efficiency, summarizing complex guidelines, drafting clinical notes, massively improving patient education. The potential is practically limitless, which frankly is exactly why we absolutely must build these systems correctly.
Section 2. Choosing the right architecture. Choosing the framework.
And this brilliantly illustrates our main options when we compare prompt engineering, RAG, and fine-tuning. For healthcare, a clear winner usually emerges. Prompt engineering, it's cheap and fast, but kind of limited. Fine-tuning, on the other hand, actually modifies the model's weights. It's super powerful for specialized tasks, like formatting standard medical data, but it can cost up to 50 grand and requires thousands of clinical examples. For most medical chatbots, RAG, or Retrieval Augmented Generation, is absolutely the sweet spot. It grounds your bot in factual documents, completely avoiding that $180,000 mistake we talked about earlier.
So, how does RAG actually work? Let's quickly break the basic pipeline down chronologically. First off, you load your authoritative documents. Think things like the Gale Encyclopedia of Medicine. Second, you split, or chunk, that text into manageable pieces. And third, you store those pieces in a specialized vector database. Basically, this whole process ensures your chatbot is looking up real medical facts instead of just, hallucinating answers.
Bridging the gap from theory to the clinic, here's the actual Python code used to chunk a medical text. We're using a tool here called a character text splitter. Notice that chunk overlap setting? That is incredibly crucial. If we don't overlap our chunks of text, we run the massive risk of accidentally cutting a semantically coherent medical passage right in half. That could literally strip away vital context before the AI even gets a chance to read it. Right, so once we have those chunks, we convert them into numeric representations. These are called embeddings. And we store them securely in vector databases, like Pinecone. This setup allows for super high-efficiency, real-time medical retrieval. So when a patient asks about a symptom, the system instantly finds the mathematically closest, most relevant piece of medical literature and feeds that directly to the language model.
Section 3. Protecting patient data. Securing patient PHI.
Now, what's really interesting about this slide is how we handle sensitive info. When a user types highly sensitive protected health information, or PHI, we can actually place a policy proxy right in the middle. Tools like Agent Shield automatically detect and redact up to 12 types of personally identifiable information, stuff like emails and phone numbers, before it ever even hits a third-party server. The LLM gets the context it needs to actually help, but the user's real identity never leaves your secure infrastructure.
To keep you completely safe, our sources outline some really stark differences in deployment. Public LLMs like your standard ChatGPT, high-risk, and multi-tenant. You should use those only for non-PHI tasks, like general literature summaries. For actual patient data, you've got to use isolated LLMs. These are tenant-scoped environments like Azure OpenAI, where the vendor explicitly agrees not to train on your data. Above all, you want to adopt a metadata-first design. Only send semantic metadata, codes, and aggregates to the model, and keep that raw PHI locked safely inside your own boundary.
Section 4. Ensuring clinical safety. Beyond AI empathy.
Okay, we really need to shatter the illusion that an empathetic-sounding AI is automatically a safe AI. Research from Penn State is super revealing here. They found that models score near 100% on surface acknowledgement, meaning they sound incredibly warm, nice, and empathetic. But their therapeutic appropriateness completely collapses in crisis scenarios. Standard alignment actually trains these models to offer false reassurance, or it makes them ground patients prematurely during uncomfortable but necessary protocols like imaginal exposure and PTSD therapy. Essentially, they get high marks for sounding polite, but fail catastrophically at following the actual clinical manual. To fix this, researchers propose a rigorous 5-axis evaluation framework. Before you even think about deploying, your bot must prove a few things. 1. Protocol fidelity. Does it actually follow the therapy steps? 2. Hallucination risk. Could it fabricate a clinical claim? 3. Behavioral consistency. Does its stance randomly shift mid-conversation? 4. Crisis safety. How does it handle severe distress? And 5. Demographic robustness. Does it perform fairly across diverse populations? You absolutely need active clinical safety, not just a model that passively refuses to answer a prompt.
Section 5. Testing and deployment. Real-world production.
Let's move to and see how this all builds together. Launching a medical chatbot requires incredibly robust production patterns. You absolutely need a human-in-the-loop architecture. The model suggests, sure, but a clinician confirms. You need A/B testing with clinical guardrails so you can instantly revert if hallucination rates spike. And of course, you must comply with strict regulations, things like the Healthy One algorithm transparency rule in the US and the comprehensive risk management required by the EU AI Act. These are not just tech choices, folks. They are literal, non-negotiable patient safety requirements.
Ultimately, building for healthcare isn't about just slapping a general chatbot onto a medical website. It's about precision architecture, aggressive data protection, and a relentless focus on clinical fidelity. So, is your AI roadmap truly ready for the complexities of human health? I really challenge you to take this structured blueprint back to your own organization, audit your current systems, and elevate your standard of care. Thanks so much for exploring this with me on this explainer, and keep building responsibly.